another piece of data. So I'm only going to do one. Well, I've got lots of other data sets, but let's just do one which is a little bit more complicated. So this other data set that I'm going to do is based on meat and meat hanging up. When you kill animals, you hang them up to, I don't know what you call it, cure or season, or anyway, you just hang them up so that the blood comes out of them and the body settles. So that's what you see in all the films when you see the cold rooms and the whole sides of beef or pork or whole lambs hung up in a butcher's on a meat hook, usually from the ceiling, and the blood settling and the meat's curing and getting to its aging. That's what the butchers call it. You're aging your meat. So here you've got the time after these two, they're done in pairs. So it's the time after a steer, after a cow has been killed, and you've got the pH of the carcass. So it starts off being relatively neutral, which is what your blood is, and then it goes down to being more acidic as time goes on. So after 8 hours, you end up with a certain amount of acidity. So in this case, it's gone to a pH of 5.3. Let's just go through the same process that we did before. We'll do a scatter plot. Pop it in here. So which one's the x-axis? Which one's the independent variable? Time or pH? What's the outcome variable is the easiest one to do. Yeah, time is on that side, pH is on the other. That's okay. Here's the plot. I can do my line of fit as a linear thing. It scores 0.933. Everything looks good. There we go. You happy with that? Does that look a good fit to the data? It's got a high R squared. The thing is, the equation is y equals 7 minus 0.21 times x. What did I click to get the fit? So if I click on this, double click on the graph, click on this button here, which says add fit line at total. Okay. So there I've got a line, I've got the fit, everything looks good, so let's do it. Analyze. Regression, linear. Dependent variable is pH, independent is time. I'm going to do my coefficients as usual. Cancel, not doing that. I'm going to save the unstandardized predictive values, the unstandardized residuals and the standardized residuals. Oh, I'm not doing cooks. I'll do leverage. Okay. Press OK and go. Now it's got my method, it's got my R and my R squared. I've got the significance of my data, it's less than 0.01, everything's good there. I've got the constant is 6.996, but it goes between 6.773 and 7.220. And I've got the time. So the gradient is minus 0.209, and it goes from minus 2.54 to 1.63. And here's my residuals. Everything looks great. I can take pH out and I can do the standardized residuals. Let's put these in and go OK. Now I look at the standardized residuals and what can I see? Do I see them randomly scattered around like I did the first time? No, they've got a curve in them, haven't they? So I think I need to go and look at that slope and this graph again. If I look at it, it's fairly clearly a curve. If I'd have double clicked on this, and instead of when I did the, that's the fit line. That's not the fit line that I want. I want to delete that one. I want to add fit line at total, but I want to choose it. So if I do quadratic, which is what it's done there, close. Let's get rid of this one. Delete. Delete. Good. So if I'd have done quadratic, that's a better fit by putting a curve in. So that's a bit annoying. It's not a straight line, but everything that told me when I did that regression that it was fine. I've got a good R² value and I've got a good R value. I've got a significance on the ANOVA. I've got significance on the t-tests for the constant and for the time. Everything looks fantastic. But when I go and plot the residuals, I've got a curve in it. So this is why it's important to use SPSS and to calculate the residuals, because you can have something that looks like it's a very good regression and is actually not. So let's do it again. Now, how can I make curved data into a straight line? I'm going to go back to this set of data and I'm going to delete all these columns because I don't want them. Delete, that's good. Now, what do you do to turn curves into straight lines? What have you seen people do? Actually, let's not do that. Yeah, they take logarithms or reciprocals. So we're going to do a log one. So what I'm going to do is go to transform and what am I going to do? Computer variable. So I'm going to compute a variable which is going to be called log time. And oddly enough, it's going to be dependent on time, actually, and it's going to be the log. So if I put all of the mathematical functions up, I go down here, so I can do the log 10. So it does. So it tells me log 10, puts a question mark, and asks me which variable I want to put in. I want to put time in there. So it's now going to do the log 10 of time. Press OK. So now, when I go to my data, I have time, pH, log time. So now I can do the analysis again. So I can go down and I can do regression. I can do linear. Instead of having time here, I put log time in there. Everything else is the same. Continue. I calculate all the same outputs. Go OK. Now, this time, my R is even higher than it was before, and my R² is even higher. I'm still significant on my test, still significant on the t-tests for the constant and the gradient, but now the gradient's dependent on the logarithm of time. And now, if I go to Chart Builder and I do the standardized residual against I want to do against time or log time. Actually, let's leave it as time and see what that looks like to start with. Okay, that's fine. Is there any kind of pattern in there? Can I see the curved thing that I saw before? No, so that's fine. So now I've done the right regression by doing the logarithm of time against pH rather than by doing time itself. So that's an example of doing linear regression on a transformed variable. And that is as much as I want you to be able to do at this particular point. So either, most of the time it will be logs, Occasionally, it might be reciprocals, such as in enzyme kinetics. You do a double reciprocal plot. So you do 1 over x and 1 over y. The only thing you need to remember is when you transform your data back for your confidence intervals. So the model here, the confidence interval for the gradient is based on the logarithm of time. So I have to take the anti-logarithm of this and this to show what the actual values are. So they'll come back, and the time was minus 0.209 was the slope. So that should correspond roughly to this minus 1.671. Actually, it can't be a time of minus 1. Oh, yes, slope is that. Yes, ignore the sign. So if I take the anti-log of those, I can work out what the confidence boundaries are in actual time values between the two. But usually I'm going to ask you the gradient and the constant. I'm not going to ask you to back transform it. Right. That is as much as I want to do. I mean, I can run around and go through all of the other examples. I have lung capacity, mold growth. It's always the same. Go to analyze, you go to regression, you go to linear, you pick on statistics to do confidence intervals. In this case, the size of the colony, the radius is the dependent variable, and the time, again, the days from inoculation, is the independent variable. And whoops, cancel. I want to calculate the standardized residuals. I'll forget calculating the rest of those things. And press OK. So in this case, R is 0.995, R squared is 0.991. It's significant again on the p-value. The constant is not significant in this case. So the reason that it's not significant is the constant could be minus 0.888 or positive 4.3. So that confidence interval includes 0. So therefore, there is not a significant value of the constant. 0 is the origin, is a perfectly valid example within this case, and that makes sense. That on day 0, the radius of the colony is 0 because it hasn't grown yet. So you'd expect it to go through the origin. The slope is somewhere between 1.9939 and 2.535. So that's how fast it grows per day. It's somewhere between those two, with an average of 2.237 millimeters. I can plot the residuals just to check that things are behaving themselves as they should do. Scatter plot. Scatter plot. Drag in. Standardized residuals, days from inoculation. Press OK. Are they scattered around randomly? Kind of. There's so few points that there's a bit of an up-down, actually. Perhaps there is a bit of a curve there, but it's too small a data set to be sure. You probably need at least 10, probably about 20 points for you to definitely identify that there's a curve in it. Right. So I am done for